going to speak about a hypothetical cell to start, and we're going to look at our ions in question individually. So we're going to start by looking at potassium, what happens with potassium. So we're going to take a neuron that only has the movement of potassium. Okay, now this is not what happens in our physiology. We know that in actuality, both sodium and potassium are moving, but in order to sort of dissect this and really understand each of the ions individually, we're going to start by looking at them in a hypothetical cell where they're the only ions that are moving. So we start off with potassium. Potassium, we know, is high in concentration inside the cell. What was the main driving force for that? Why is potassium higher in the cell? Not necessarily. They have more channels. That's a good guess, but that's not exactly why potassium is higher. Why is potassium higher inside the cell? So those channels are actually leaking potassium out. But what's making potassium go in? What did we say is responsible for setting up these concentration gradients? That primary active transport mechanism. The sodium-potassium pump, right? So the sodium-potassium pump is why we have more potassium inside the cell. It's really important to understand that. So it's pumping potassium into the cell, and so we start off with potassium at a higher concentration inside the cell, a lower concentration outside the cell, and that gives us a chemical driving force where potassium wants to move out of the cell because of its natural concentration gradient. So according to its CDF, potassium can move out of the cell from a high concentration to a low concentration. Now again, this is a hypothetical cell. We're only looking at the chemical force here, and then we're going to add the electrical force because we know from prior knowledge that both of these forces are acting on a cell, not just the chemical, okay? So let's add the electrical force here as well. So we got potassium moving into the cell, right? Now it's leaving behind that unopposed negative charge because it was moving out of the cell, right? It's a positively charged ion. It's moving out of the cell according to its chemical force. And so now we create this unopposed negative environment inside the cell where the electrical force now wants to move potassium back into the cell, okay? I'll say that again. So according to the chemical force, potassium is moving out of the cell because of that concentration gradient. But now as potassium moves out of the cell, and because it is a positively charged ion, it leaves inside this negative environment. The inside becomes more negative, and so the electrical force is actually in the opposite direction, trying to pull potassium back into the cell, okay? So looking at just potassium alone, we have a CDF going out and an EDF going in, okay? So when we combine those forces and potassium gets to its equilibrium, that value ends up being about negative 94 millivolts. So after potassium moves in and out and it finally gets to that stable equilibrium, what does that equilibrium represent? What's happening with potassium? What's happening with potassium here? At negative 94, what's happening with potassium? Is it moving into the cell, out of the cell, or is it not moving? It's not moving. Perfect. It's not moving. So at negative 94, that is when potassium gets to its equilibrium, and that is when the forces are exactly the same and they're exactly opposite, and so potassium stops moving. Okay? That's kind of the first piece of the resting membrane potential. So we got a chemical force. We just to remind ourselves of what the equilibrium potential is. It's the potential at which there's no net movement for the ion because the chemical driving force is equal and opposite to the electrical driving force, and so there's no net ECDF, so no net movement. Okay. Now let's look at sodium. So we talked about potassium. We know that it really wants to move into the cell and out of the cell according to those forces. Let's look at sodium. Again, we're taking a hypothetical cell and we're thinking about only the movement of sodium in this hypothetical cell. Now, we also want to remind ourselves of the relative ion distribution of sodium. Sodium is higher in concentration outside the cell, and it's being opposed by that negative chloride. Potassium is going to be higher in concentration inside the cell and opposed by those anions, and this is mainly set up by that sodium-potassium compound. So we're again going to start off by looking at just the chemical driving force for sodium. So sodium is higher in concentration outside the cell, and so naturally it wants to move inside the cell according to its concentration gradient. And so that is the first part of its movement. We can then add in the electrical force to that equation. So because sodium begins to move into the cell, we have that positive charge going into the cell. We create an excess of positive inside the cell. And so now we also have an electrical force for sodium to move out of the cell because it's going to move away from its like positive charge, right? They're both positively charged. If the inside becomes more positively charged, sodium wants to move out according to the electrical force. Okay, so when you combine those forces, we see a very similar scenario as we saw with potassium, chemical force opposing the electrical force. And then sodium eventually reaches its equilibrium at about positive 60 millivolts. So this is the exact membrane potential at which there is no longer any movement for sodium, where its chemical driving force is exactly equal and opposite to its electrical driving force. Right? Those are two important values for us to keep in mind, that negative 94 for potassium and that positive 60 for sodium. Okay, so we had chemical force to move into the cell and electrical force to move out of the cell. Now, initially, there's a stronger chemical force, but eventually the electrical force is going to continue to rise, okay? And so we're going to look at what happens with sodium because of the difference in membrane permeability. Okay, so sodium is going to be kind of the exception as we move on. So let's put everything together here and look at the two chemical driving forces. So sodium eventually moves out. Potassium wants to move out. Sodium wants to move in according to those chemical forces, right? Reminding ourselves that the concentrations of sodium is higher outside, the concentrations of potassium are higher inside the cell, okay? Now, this is where things get a little bit more interesting. This is where we take the permeability into account. So at the beginning of this discussion, we mentioned that the membrane is more permeable to which of our two ions? Potassium, right? To potassium. So essentially, we have more potassium channels on this membrane, as we can see in this image, right? So there's more of an opportunity for potassium to move and less of an opportunity for sodium to move, okay? Now, so because we have that positive charge, right? Sodium wanting to move into the cell, but it does so at less of a permeability. Potassium wants to move out of the cell, but it does so at a greater permeability. That is going to influence that negative environment inside the cell. Okay, think about it. We got more positive leaving than we have positive coming in. So what's the inside of the cell going to start to look like? Positive or negative? We got more positive leaving and less positive coming in. It's going to start to look more negative. Yeah, so that's how we start to get that negative environment when we consider the movement of both of our ions because of the difference in the permeability, okay? Okay, so just to kind of recap that here, we had an electrical force developing, sodium going into the cell, potassium also moving into the cell according to that electrical force, okay? So sodium goes into the cell, potassium goes into the cell, and remember, the electrical force is based upon the charge. So because the inside of the cell gets really negative, as we just saw, and these are both positively charged ions, they both have an electrical force to try to get to that negative environment inside the cell. So the electrical force of both these ions are going to be in the same direction. But their chemical force is going to be in the opposite directions, right? The chemical forces are based upon their concentration gradients. And we know there's more sodium out, more potassium in. So sodium wants to move in according to its concentration gradient, and potassium wants to move out according to its concentration gradient. So what we end up with is a ECDF, right, a combined force for sodium that is in the same direction. Its chemical force wants to go in because of that concentration difference. Its electrical force also wants to go in to get to that negative environment. But for potassium, the ECDF is in opposite directions, okay? We have a stronger chemical force wanting to go out because of the concentration difference, and we have a weaker electrical force wanting to go in because potassium wants to get to that negative environment inside the cell, okay? So because of the combination of all of these factors, what we end up with is a strong force for sodium to move into the cell, right? We just combine those two forces in the same direction, and a weak force for potassium to move out of the cell because it has that opposing charge, that opposing force that's trying to drag it back